Welcome to the class. Today we are going to talk about scaling up graph neural networks. And in particular we will be interested in how can we build graph neural network models that can be applied to large scale graphs, and what kind of techniques can we use to be able to do that. So let's first kind of define and motivate the problem. So there are large graphs in many modern applications. If you think about recommender systems, for example, systems that recommend you products at Amazon, systems that recommend you videos to watch on YouTube, pins to look at Pinterest, posts to examine at Instagram, and so on, you can think of this as a way where we want to connect users to the content, products, videos that they might be interested in. Right? And you can think of this recommendation task as a way to do link prediction in this large bipartite graph where you have, hundreds of millions, billions of users on one end. On the other side, you have tens of millions, hundreds of millions, tens of billions of items on the other end, and you would like to predict what movie, what video, what product is interesting for what user, and you can formulate this as a link prediction task. Another example where graph neural networks can be very well applied is in social networks. For example, Twitter, Facebook, Instagram, where you have users and friend and follow relations, and you want to ask about how do I want to recommend friends to each other at the link level. Do I want to do some kind of user property prediction? For example, predict what ads different users would be interested in, or predict what country they come from, or perhaps I'm doing some kind of attribute imputation in a sense that maybe some users tell me their gender, but I don't know the gender of other users and I want to predict it. And again, in this case, these networks have billions of users and tens to hundreds of billions of edges. And then another application that can be motivated by what we are going to talk about today is a notion of heterogeneous graphs. And for example, you can one such a data set is called Microsoft Academic Graph, which is a set of 120 million papers, 120 million authors, as well as their affiliations, institutions, and so on. So this means now you have a giant heterogeneous knowledge graph on which you can try to do a lot of interesting machine learning tasks. For example, paper categorization, which would be predict what category, what topic the paper is about, recommend collaborators to authors, predict what papers should cite each other. You can imagine this to be very useful when you are writing a new paper or doing a new piece of research. And these are again machine learning tasks over this giant heterogeneous graph. And more broadly, right, we can think about knowledge graphs coming out of Wikipedia, coming out of Freebase, where again we have 100 million entities and we want to do knowledge graph completion tasks, or we want to do knowledge reasoning tasks over these knowledge graphs. And what all these applications have in common is that they are large scale, right? That number of nodes is in millions to billions, and the number of edges is, I don't know, tens or hundreds of millions to tens to hundreds of billions. And the question is, right, like if we have these types of large-scale graph, this set of large-scale data, and we would like to do tasks in all these cases that I have motivated, we can do kind of node-level tasks in terms of user, item, paper, classification, prediction, as well as pairwise level tasks like link recommendation, link prediction, and so on. And the topic of today's class will be about how do we scale up GNNs to graphs of this size, right? What kind of systems, what kind of algorithms can we develop that will allow us to learn over this kind of massive amounts of data? So let me explain why is this hard, or why is this non-trivial. And it will become very quickly clear that we need special methods and special approaches. right? When we have a big data set, let's just think in general, like in a general deep learning framework, when we have a large number of n data points, what do we want to do? Right? In general, our objective is to minimize the loss, the average loss over the training data. So if I have n training data points, then, you know, I have this summation from 0 to n minus 1, where for every data point I'm asking what is the loss of it, right? What is the discrepancy between the true label, the true prediction, and the prediction made by the model. And I would like to compute this total loss under the current model parameters theta, so that then as I can compute the loss, I can then compute the gradient with respect to the loss and update model parameters in such a way that the total loss will be minimized, so basically the model parameters will change, which means model predictions should change such that the loss, the discrepancy between the true labels and the predicted labels gets smaller. And notice what is the point here. The point here is that we have to sum up these loss contributions over all the training data points, right? Because the number of training data points is too big, what we then do is we would actually select small groups of m data points called the mini batches, and then approximate this big summation with smaller summations where I only goes over the points in the mini batch, right? Over, I don't know, 100,000 data points we have sampled, and then compute the loss over it, and then make a gradient step. This means that our loss, our gradient will be stochastic, will be imprecise, will be a bit random, because it will depend on what exact subset of random points m have we selected, but it will be much faster to compute because m, the size of the mini batch, will be much smaller than the total amount of data. So our model will converge faster. Now, what could you do in graph neural networks? You would simply say, if let's say I'm doing a node level prediction task, let me subsample a set of nodes n and put them in a mini batch and let me learn over them. Here is the reason why this, for example, won't work in graph neural networks, right? Imagine that in a mini batch, I simply sample some set m of nodes independently. And what this picture is trying to show is these are the nodes I'm going to sample. And because the mini batch is much smaller than the total size of the graph, what is going to happen is that, yes, I'm going to sample these nodes, but the way graph neural networks operate is that they aggregate information from the neighbors, but most likely none or majority of these neighbors won't be sampled in our mini batch. So what this means is that the nodes in a mini batch will tend to be isolated nodes from each other, and because the GNN generates node embeddings by aggregating information from the neighbors in the graph, those neighbors won't be part of the mini batch, so there will be nothing to aggregate, and whatever gradient we compute over isolated nodes won't be representative of the full gradient. So this means that the stochastic gradient descent won't be able to train effectively on graph neural networks if we do this naive mini batch implementation where we simply select a subsample of nodes, as I illustrated here, because nodes in the mini batch won't be connected with each other, so there won't be any message passing to be able to be done between the neighbors, and the entire thing is going to fail. So another way how we could do this is to say, let's forget mini batching, let's not select a subset of the training data to compute the gradient on. Let's do what is called full batch implementation, full batch training. And the problem with full batch training is the following, is that you can think of it that we generate embeddings for all the nodes at the same time. And the important thing here is to notice that we have embeddings of the nodes at several layers, right? We start at layer 0, which means the embedding of the node is just the node features. Then we propagate through the first layer and we get the embeddings of the node at layer 1. Now, to compute the embeddings of the node from layer 2, we have to aggregate the first layer embeddings to compute the second layer embeddings. So what this means is that you would first load the graph in memory and all the features, and then at each layer of the GNN you would compute the embeddings of all the nodes using the embeddings of all the nodes from the previous layer, right? So that now if I'm computing the layer K, I need to have all the embeddings of all the nodes stored for layer K minus 1, so that whenever I'm creating the next layer embedding of a given node, I check who its neighbors are, I take the previous layer embeddings for those neighbors and aggregate them to create the next layer embedding. And because of this recursive structure, I basically create I need to be able to keep in memory the entire graph, plus the embeddings of all the nodes from the previous layer, as well as enough memory to create the embeddings of all the nodes for the next layer. And then once I have that, I can then compute the loss and I can perform the gradient descent. So the way you can think of this is I start with the initial embeddings of the nodes, I perform message passing, create the embeddings of the nodes at layer K plus 1. Now I put this here and call this layer K. Again, do the message passing to get to the next layer. And this would be what is called a full batch implementation of graph neural network. And why is full batch implementation problematic? It is problematic for two reasons. One reason is that it takes super long and it's kind of time-wise, data-wise inefficient to do full batch training. But imagine, you know, you have all the time in the world, so you say, I don't care if it takes a bit longer. Even with that, it is still impossible to implement a full batch training for large graphs. And the reason for this is because if we want the training to be to be kind of in the order of magnitude of what we are used today, then we want to use GPUs. We want to use graphic cards to do this, right, for fast training. But GPUs have a very special kind of super fast memory, but they have very little of it. They have about 10 to 20 gigabytes of memory, and I think the most you can buy today is around 30 gigabytes big GPU cards, and that's, you know, considered super state-of-the-art. Nobody has those graphics cards, right? But the point is that entire graphs and entire features, if you have a billion nodes, will be far, far bigger, right? If you have a billion nodes and you just spend, let's say, 1 byte or you have, I don't know, 100 bytes of features per node, it will easily, you will need a terabyte of memory, 10 terabytes of main memory, which is the amount of memory we can get today for large servers using CPUs. So the point is CPUs have slow computation, large amount of memory, GPUs have very tiny amount of memory, but super fast. And the point is, if you want to do full batch, you need to fit all the features, all the embeddings, and the entire graph structure into the GPU memory. And 10 gigabytes is nothing. It's less than what your iPhone has memory. So it is so small that we cannot scale full batch implementations beyond a few thousand node networks, and definitely not to millions and not to billions. So this motivates the lecture for today, right? So the lecture for today will be, how can we change the way we think of graph neural networks? How do we implement the training? How do we change the architecture so that we can scale them up to large graphs of billions of nodes, so that we can limit this issue with small GPU memory, and that we can limit the issue that naive implementation of mini batching just doesn't work. So I'm going to talk about two methods. Basically, in this lecture, I'm going to talk about 3 different methods. 2 of them will be based on performing message passing over small subgraphs in each mini batch. So we are going to change how we design mini batches. And this will lead to fast training time. One is technique called neighborhood sampling, and the other one is technique called Cluster-GCN. And then I'm also going to talk about the third method, which will be about simplifying the GCN in such a way that we simplify the architecture so that computation can be efficiently performed on a CPU, and because CPU has a lot of memory, we can scale to large graphs.